Okay, so we're going to talk about an ideal transformer. And an ideal transformer is often drawn this way. Now I'm going to do a dot convention here. And it's important to understand here where the dots are, because this is actually going to affect answers. And we'll do an example showing how this can affect your answers. Most of the time what it does in your answer is it's not going to affect the number, it's just going to affect whether it's positive or negative, is what the dot convention is going to play a role into. I'm just finishing drawing this here. Okay, so an ideal transformer, I'm not even putting L1 and L2 in here. You'll often see these double lines in here indicating it's an ideal transformer, and you'll see this N1 to N2. So N1 to N2 is referred to as the turn ratio. And it literally means how many turns you have on one side of the inductor compared to the other side. So let me just give you an example here. This is a kind of a cheap way to make an inductor. It's not really how inductors are made, but it will just kind of at least illustrate what I'm referring to here. So basically, this is going to be basically solid metal here. This might be, for instance, like iron. It's usually a ferromagnetic material is what you want there. And so then I'm going to have, on my primary side, I'm going to have a coil coming in. And that would be my primary coil side. So I'd have a plus minus V1. And then this would be my secondary. Now, if you want to look at it here, the turns here, if you think how many times have I wrapped around this thing here. So I've wrapped around 1, 2, 3, 4, 5, 6. So I have 6 turns on the primary side, which is not, as far as an inductor, that's not going to be good enough for a transformer, but we're just illustrating how we get these turn ratios here. And then on the secondary side, we have 1, 2, 3 turns. And so the turn ratio here would be 6 to 3, but we also like to reduce that down as much as possible. So my turn ratio would be 2 to 1 for this transformer. And as far as how you know what their dot convention are, is it has to do with how these things are winded around the iron core. So this again would be a turn ratio of 2 to 1. So when we see these turn ratios, it's literally meaning kind of how many times we've wrapped this coil around here. Now, you can read in the text, and they talk about a lot of the mathematics on behind where you can get some of this information. But what I like to do here, this is some load here, I'll just say load, is to give us voltage and current relationships here. And it's easy to mix these up, but if you remember these, the examples that we'll then do are going to be relatively easy. Now, there is one other definition that we have here. There is this quantity called A that is defined sometimes, and this is equal to N2 over N1. And so sometimes on a transformer you'll see just a single number. And if that single number is on a transformer, that's like can sometimes be the letter A. Now, most transformers now, the specs, the way they're written, they just tell you what they are. It's like, so it's like input is 115, output is 15. Let me just even show you that. Let's go to DigiKey here and show you what I'm referring to with a power transformer. So let's look up a power transformer. Power transformers. And I'm just going to pick some random one here just at the beginning here. I'm not really worried too much about it. But, if I pull up the data sheet for this here, it gives me what a circuit diagram looks like. And notice it's got two coils on the outside there. But it doesn't really have anything about, the turn ratio here. But what it does have, for instance, is it gives you the maximum power of 1.1 volt amp. It tells you, okay, what do you put in on the primary side? Well, it's 115 volt at 50 or 60 hertz. And then the secondaries, well, 5 volts, 0.11 amp each. So there's two coils on the secondary side, and so it gets 5 volts. Now, the reason you can do that is you could connect this in series so that you could get 10 volts. In other words, you could get 115 down to 10 volts. Or you could connect them in parallel and get 115 down to 5 volts, but have it at 0.22 amps. So that's often the reason they do that. You'll see some transformers where they'll have two coils on the primary side, and that's for if you want to have a transformer that's doing like 230 on the input versus 115. And it talks about, hey, used independently up to 300 volt distance or in series for double voltage or in parallel for double current. Needs a electrostatic shielding. I'm just trying to see if there's something else here on these here. Yeah. The other thing you want to look here is, what standards does it meet? It's considered a class 2 transformer. And the reason you want to know some of these standards is you often want to fuse transformers unless they have their own internal fusing or their own internal things, because there will be some transformers like where no fusing is necessary. Oh, here it is, inherently limited. That's what I was looking for, no fusing required. So some transformers are not inherently limited, and so you actually have to put a fuse on them. Otherwise you can cause very dangerous situations. When I mean dangerous situations, I mean you can literally, have it where the thing overheats, causes fires, and all sorts of stuff. But this is typically how we get them. Is that it's not that we're giving a turn ratio. We're just basically giving the spec, 115 volt down to 5 volt. Okay, so we've got that. But let's go ahead and go back here and look at how we can use these turn ratios to go ahead and compute some output voltages. So there's a couple very important equations here that you want to keep in mind. And as I said, I'm not going into the theory on where these come from. This is the first one here, is that V1 over N1 is equal to V2 over N2. And one of these, to me, it's one of the most important equations here, because what we can see from this is that if you're looking about what the output voltage is, we get that this is V1 N2 over N1, or A times V1. But the reason I point this out here is if we look at this particular example here, this is a step down. And by writing it 2 to 1, it steps voltage down by a factor of 2. Now, on the flip side, if we had something like a turn ratio of 1 to 3, this would be a step up transformer. And if you had an input of 10 volts, it would output 30 volts. So, very simple here. The other extremely important equation that we want to keep in mind is the current one, is that I1 N1 is equal to I2 N2, which should not seem too surprising for us, because we said in the previous video that if voltage goes down, current should increase. So let's look at this here, going back to this example here. So if we're looking at what I2 is, I2 would be I1 N1 over N2. Well, in this case here, for my step down, I'm stepping the voltage down by a factor of 2, but then I'm stepping the current up by a factor of 2. And again, we shouldn't be too surprised by this, because power, we said, is conserved. Power is equal to current times voltage. So if we step the voltage down by 2, we need to step the current up by 2. Now again, when we do these ideal transformers, we're assuming no power loss, but you might say these aren't very accurate assumptions, and you're absolutely right. They're not incredibly accurate, but they are good for kind of some initial kind of rough estimates to get yourself in the ideal ballpark of what an answer should be. You know, because if you don't really know what an answer should be, how do you know if you're right or wrong? One other application of transformers, of ideal transformers, is actually to change load impedance. So if you're specified Z in and Z load, you can find A for max power transfer. And what does that mean? Well, if we go back here, there might be, for instance, a 4,000 ohm impedance here, and maybe my load is only 8 ohms. Well, I don't want to necessarily connect that 4,000 ohm directly to the 8 ohm, but I can use a transformer, solve for A. Let's even do that. 4,000 ohms was my input, A squared, which is equal to my output, which I said was 8 ohms. So we can now design a transformer to transform my signal so that I get max power transfer to the load. And so doing this, we just simply solve for A squared, which is, of course, 8 divided by 4,000. And so A squared is equal to 0.002, which means A is equal to 44.7 milli. And there's no units for A, so I'm just putting little, well, that gets a little confusing. You might think that's meters. Let's go ahead and write it as scientific, times 10 to the negative third. And so if we're thinking about what my turn ratio should be, well, we had here that, make sure I have it, yes, N2 over N1 is equal to A. So we have that N2 over N1 is equal to 44.7 times 10 to the negative 3. And so I like to think of it as N1 is equal to N2 divided by 44.7 times 10 to the negative 3, which that would get me N1 is equal to 22.37 N2. And then as far as the turn ratio, you just make life easy. Let's just make N2 equaling 1. And so then, just rounding here, we'd go ahead and say let's let N1 equal 22. So if I had a 22 to 1 transformer, I would be able to essentially make this 8 ohm load see an 8 ohm impedance as opposed to a 4,000 ohm impedance, so I'd get maximum power transfer. So that's another application of transformers. I have not personally used that application very often. Most of the time when I've used transformers, it's been purely for power transformers. So the next video here, we're going to look at an example of actually using the turn ratio to compute some actual voltages and currents.